The binomial distribution is a discrete distribution. It would be useful if it was continuous, because we learnt some things about continuous distributions. So that's why we want to approximate it as a normal distribution, because that was a continuous distribution. So that's the idea of what we're going to be looking at. And here's the example. A school of 1,200 students, similar to our own. Find the probability that it contains more than 150 left-handed students. So how would we solve such a problem? Of course, we could go and talk to all 1,200 students and find out, but that would take some time. So another approach is we could just take a random sample. Pick, say, 50 students, find how many are left-handed, and from that info we could then use that to estimate the probability of someone being left-handed. So let's say our sample contained 8 left-handed students. Then we'd say the probability would be 8 out of 50, 0.16. That would be our estimate. So if it's binomial probability and I let x equal the number of left-handed students, then I know the distribution would be 1,200. That's how many is in the entire population that we're interested in. And we've said the probability of success, 0.16. We want to find the probability when x is greater than 150. That's obviously a lot to find, because you've got 151, 152, 153, 154, 155, 156, and keep going up to 1,200. The complementary event would be a, smarter way of doing it. Mind you, there's still quite a few calculations there to do. In fact, that's still got 151 calculations to work out to solve that. And so that's why the approximation, the normal approximation, is useful, because rather than having to make 151 calculations. By the way, it turns out to be 0.9996. Okay, if I was to draw the polygon, it ends up looking like that. Now, I've smoothed mine out so you don't have a whole lot of sharp edges, but that's basically what the curve would look like for our distribution polygon. What we just found was the probability of it being greater than 150. So we've found the area under the curve on the right-hand side of 150, and you can see why it ended up being quite large. I mean, the vast bulk of the numbers are to the right of 150. Well, let's just look at that curve. The mode is in the middle of the distribution. It's not out at an edge. It certainly looks symmetrical. And the other key feature that I'm interested in is how it tails off very quickly. So you have that bulge in the middle and then tails off real quickly. And if you recall the normal distribution, the classic bell shape, that's what this looks like. Because it looks like a normal distribution, it seems reasonable that we could approximate with a normal distribution. Okay, so if we assumed the distribution was normal. Now remember, with our binomial distribution, we were interested in two things: the number of trials and the probability. With the normal distribution, we were also interested in two things. But those two things were the average and the variance. So let's work out the average and the variance for our binomial distribution. So remember, 1,200, 0.16. So our average NP is 192. The variance turns out to be 161.28. So if we now said it's normally distributed with that average and that variance. But the other thing you'll recall, I hope, from when we looked at the normal distribution, to calculate the probabilities, it was a lot easier to use the standard normal distribution of 0, 1. So I need to convert my x, and we use our, z-score, but that formula, x minus mu on sigma. So we want when x is less than or equal to 150. That's what we were looking for. So z would be less than or equal to 150 minus 192 on root 161.28, which turns out to be minus 3.31. And then all we've got to do is look it up in the table or use our calculator, however we end up with it. It comes out to be 0.9995. Not quite the right answer, but remember, this is an approximation. That's a pretty good approximation. Remember, the exact value is 0.9996. So the normal distribution fitted quite nicely. In fact, if we were to work out the error, it's out by 0.008%. So So it's quite a good approximation in this case. So, all right, so when is it okay to approximate with a normal distribution? Those three key features that I talked about before. We want the mode to be in the middle of the range of values, so not at the extremity. We would like it to look symmetrical about that mode. And the other key bit was the frequency tails off. So we get that classic bell-shaped curve. Now, let's have a look at a few and work out which ones would be good. This is one where the probability of success is 0.125, and I've just increased the number of repetitions from 10, 20, 30, 40, 50. So it goes along that way. Now, when you look at 10, we can see, well, that's not going to be any good because it starts halfway up here. So we don't have a symmetrical curve or anything like that. Whereas the last one, it's starting to tail off, but it's, that's probably not too bad if we had n equals 50. If I draw up a table there, the only information we know, remember, about the binomial distribution, n, p, and q. So those three pieces of information for each of those curves, and I've multiplied NP and also NQ. As we go along, really, the only one I could say with confidence would be that last one, 50. 40, it's close. Maybe you would, maybe you wouldn't, because you can see it's starting to tail. But the other three, no, definitely not. Okay. Well, if I change the probability to 0.25, that's how our graphs change. So now, 30, 40, and 50, so the last three look okay. The second one, maybe, it's probably right on the boundary. The first one, again, still no good. 0.375. And now, other than the first one, they all look okay. They've all got those features we're looking for. And 0.5, so when we get it right in the middle there, they all seem to be okay. The first one, again, you might debate about, but it's starting to look okay with 0.5. So as a guide, if you look at each of those tables, the difference when I've gone from tick to cross, if you like, tends to be at 5. If NP or NQ is 5 or less, then we tended to get a graph that was no good. Around about 5 is starting to look okay. So that's a general guide. So, because remember, we'll know N and we'll know P. So it's easy enough to check if NP is bigger than 5 or NQ is bigger than 5, and then we'll know, yep, this will be okay to use a normal approximation to. Technically what we're doing here, when we're approximating, the bins, do you remember what the bins are in statistics? The bins are basically the numbers underneath, so what you put in. So the classes, things like that. Now, our ones were one apart. So if we're integrating between A and B under the polygon, what we're really doing, because remember the rectangles were the histogram. And the rectangle, that number is in the middle of the rectangle. So you would have half of the class on the left-hand side of the first one, and half of it on the right-hand side. We're saying ours are width of 1, so that theoretically what we're finding is the integral actually not from A to B, but it's actually A minus 0.5 to B plus 0.5 for the rectangles. That's what we're estimating it with. So as I say, it might be more obvious if you think of those rectangles of the histogram. If you have a really small sample, then we might take that into account. So when we look up our values, we don't go between A and B. We'll go A minus 0.5, B plus 0.5. Now, that's really just for small samples. Once you've got lots of them, that 0.5 is not going to make much of a difference. So we don't worry about it. So 17C.